So maybe we can start this session of NCTS Algebraic Geometry seminar. So today we're very happy to have Philip Engel from University of Illinois in Chicago. And then he is going to talk to us about the boundedness of abelian vibrations. So yeah, please start.
Thanks. Yeah. Thanks so much for the invitation to speak. Yeah, so I wanted to start just by defining what do I mean by boundedness of some family of projective varieties. So suppose that I have some set um, of projective varieties indexed just by some arbitrary set. We'll say that um, that it's bounded if all of these varieties appear in some finite type family. So if there exists, let's say some curly x over some curly t, a um, family of projective varieties, and then the key point here is that over the base t here should be finite type, quasi-projective, um, finite type quasi-projective variety, such that for all I in I, we see the isomorphism class of xi as some fiber. Um, so actually, let me do Roman xi is isomorphic to curly xt for some t in the base. Okay, so that's a notion of a collection of projective varieties being bounded, and we can weaken. So we can sort of weaken this condition um, isomorphism um, to other notions. So for instance, we would say that the collection is birationally bounded if instead of um, having isomorphism, we allow a birational isomorphism to some fiber. Again, for all I and I, there's some T and T, such that we have such a birational isomorphism. And, even we could sort of weaken this notion further. For instance, we could ask about topological boundedness. In other words, like, are there only finitely many topological types, say, of varieties that appear in our given class of projective varieties? So a basic question is which classes of projective varieties are bounded? So there's a few famous examples. One would be subschemes, say, of Pn with fixed Hilbert polynomial. Okay, so or if we want varieties, we could take subvarieties of fixed volume, for instance, with respect to the line bundle O of 1. Another famous example are smooth Fano varieties of fixed dimension. And a sort of non-example, so a non-example might be K3 surfaces or abelian surfaces? Okay, so the reason, so the non-example for boundedness. So the reason is just that we have infinitely many different moduli spaces of K3 surfaces. So we have the space of degree 2D, K3s, say XL. And we have a different family for infinitely. So we have infinitely many different quasi-projective families of K3s, one uh, for each positive integer d greater than or equal to, let's say, yeah, d greater than 0. And for K3s, sorry, so these are for K3s. For abelian surfaces, we have, for instance, the spaces D1, D2, with D1 dividing D2. So these are abelian surfaces with a polarization of type D1, D2, which is to say that if we view the polarization as a symplectic form on the first homology, then the isomorphism class of this symplectic form is indexed by, a pair of integers, one dividing the next. Yeah, so there are countably many different families, but we can weaken the notion of boundedness. So we can weaken boundedness to the notion of deformation equivalence. So, we say that, say, two projective varieties x1, x2 are deformation equivalent if there exists S a connected base and a family X over S with X1 and X2 as fibers. And maybe we want to additionally assume that this is a smooth morphism. Or actually, I mean, we don't need to. Yeah. Just maybe a flat morphism. But yeah, like maybe, yeah. Yeah, maybe we should, let's restrict to, let's sort of assume they're smooth, and then we'll additionally impose that this F is a smooth morphism. But we could also consider, for instance, locally trivial deformations. There's various generalizations of this notion of deformation equivalence, depending on what we allow or to consider as a deformation class. Okay, so we see that, for Calabi-Yau varieties, well, elliptic curves come in a single family, so they're bounded. But already for two-dimensional Calabi-Yaus, there's some subtlety. We need to allow deformation equivalence, or we don't get finitely many classes of K-trivial varieties in dimension 2. So let me introduce some notions of K-trivial varieties. So we can define it as X, a normal projective variety, I should say. This is all over the complex numbers. um, with canonical singularities. Um, such that the canonical bundle is isomorphic to the trivial bundle. Okay, so canonical singularities means, together with this condition that the canonical bundle is trivial, means that so there exists a non-vanishing holomorphic volume form on the smooth locus, and furthermore, this volume form, holomorphic volume form, extends holomorphically to any resolution. So within this class of K-trivial varieties, we are going to break into three subclasses. So the first is that the so-called irreducible Calabi-Yaus. So we'll say that it's irreducible Calabi-Yau if the space of global sections of the sheaf of reflexive K-forms is zero for all intermediate dimensions. So that's zero between K between the dimension of X, which we will impose to be greater than or equal to 3. And this also holds for all, and the same is true for all X tilde mapping to X quasi-étal. Okay, so this requires maybe a little bit of explanation. So for a normal projective variety, we can just take the sheaf of reflexive differentials to be the push forward of the sheaf of smooth K-forms over this from the smooth locus of our normal variety. So you should just think of these as forms on the smooth locus. And this quasi-étal condition, this means unramified in codimension 1. So in particular, if X is smooth, then by the purity, Zariski's purity, if it's unramified in codimension 1, it's everywhere unramified. So that would be an étal cover. So for smooth things, quasi-étal is étal. So the word irreducible here is meant to is related to the fact that we also impose this condition on all the étal covers. Okay, so that's one class. Our next class are the so-called primitive symplectic. So we say that K-trivial variety is primitive symplectic if the space of one forms is trivial, and the space of two forms is generated by a symplectic form. So that is to say, H naught X omega 2 is the span of some single sigma, where sigma is symplectic on the smooth locus. So that is to say, it additionally is required to be closed and non-degenerate. Okay, and then the third class are the abelian varieties. So these are characterized by the property that the space of one forms has, I guess, let me do lowercase, has a dimension equal to the dimension of X. Okay, so those are going to be the three classes that we're going to think about. And the reason why these three classes are important is because of the Bogomolov theorem. So this was first proven by Bovell and Bogomolov in the smooth case and was generalized by work of a lot of people to the more singular case, which is that essentially up to a quasi-étal cover, every K-trivial variety breaks into these three pieces. Maybe I'll say x tilde to x is of the form x tilde. Well, it's some sort of abelian factor together with a product of irreducible Calabi-Yau factors together with a product of primitive symplectic factors. So these are irreducible Calabi-Yau factors. These are primitive symplectic factors. And then this is an abelian factor. Okay, so yeah, are there any questions about that so far? Happy with the Bovil-Bogomolov decomposition? Okay, so let's see. What can we say about this classification? Well, I mean, in some sense, the abelian varieties are completely understood, right? The symplectic varieties are, much closer to being understood, and the irreducible Calabi-Yau varieties are extremely mysterious. So maybe we can have an example. So of a primitive symplectic variety. So let's take okay, so this might not be the typical example
Can
that
I
you
ask just one sort of question about the theorem?
Oh, sure, yeah.
Yeah, so is the singularities of X somehow encoded in some understandable way in X tilde?
So yeah, that's a good question. I think that there's a sense in which the singularities kind of get better on X tilde. Like you could imagine a situation, for instance, where X is like has finite quotient singularities, right? Um, and then somehow by passing to this quasi-étale cover, it becomes smooth, right? But I think that there are these local covers of singularities, like the local fundamental group, or like index one covers or things like that. Actually, the index here is one because we're assuming the canonical bundle is trivial. But yeah, so I guess it's not, yeah, I'm not completely sure what's known about whether, say, like the global kind of fundamental group of the smooth locus, if it surjects onto the local fundamental groups. Yeah, that's a good question, though. Yeah, I'm not sure in what sense the singularities kind of get better, but there's also like a point at which you aren't going to be able to like do anything. So there's plenty of examples of, say, you can always pass to a terminalization, but there's going to be tons of like irreducible Calabi-Yaus or primitive symplectic varieties, just a single Bovil-Bogomolov factor that has, whatever reasonable terminal Gorenstein singularity you want, I think.
Yeah, thanks.
Hope that answers sort of. Okay, so let's give a sort of fun example that you maybe haven't seen of a primitive symplectic variety. So let's let G be any finite group. And let's say that G maps to the automorphisms of a lattice L. So L is like Z to the N for some N. Such that LC is an irreducible representation of G. Okay, so these are extremely plentiful, right? I mean, they're sort of as general as irreps of finite groups, with an integral structure on the irrep. So then, if I take L tensored with an abelian surface, and I quotient by G, then this thing X is a primitive symplectic variety. So that's a fun exercise that you can do using Shor's lemma to show that X has a unique non-degenerate symplectic form. So sort of while it's true that hypercalars are extremely rare, and there are only like a few known deformation types in each dimension, like if we allow ourselves like a few more singularities, then in fact, they're as plentiful as finite groups. Though of course, maybe notable is that there are only finitely many such representations of a finite group on a lattice of a fixed rank, because there are only finitely many finite subgroups of GLNZ. So there are only finitely many such examples of a fixed dimension here. So we'll see something like that later. So yeah, maybe I should also mention, well, this is just a direct sum of n copies of this abelian surface. So this one has a quasi-Étale cover by an abelian factor. But in the primitive symplectic case, I didn't impose that all the quasi-Étale covers are primitive symplectic. Okay, so the motivating question is, do k-trivial varieties in a fixed dimension, let's say D, lie in finitely many deformation classes? So as we said, this answer is positive in dimension 1 and 2, but it's completely unknown in dimension 3. And of course, there's no symplectic varieties in dimension 3 because it's odd dimensional. And there's only one, deformation class of abelian varieties. So it all comes down to the irreducible Calabi-Yau varieties, or the Calabi-Yau varieties, without the irreducibility hypothesis. Okay, so this is just a difficult question, and it's hard to get a handle. How do you make progress on this? You need to impose some kind of structure to get a foothold. So the most sort of common structure that people impose is that of a fibration. So what is a fibration for us? Well, it's a morphism. It's a surjective morphism of proper, or yeah, whatever, surjective morphism of normal varieties. Let me say that it's a proper surjective morphism of normal varieties with connected fibers and not sort of some kind of trivial example. So in other words, the dimension of y should be strictly between 0 and the dimension of x, so that we're not mapping to a point, we're not mapping to y, and we might as well assume connected fibers by replacing this map with its Stein factorization. So the simple observation is just that since we have that the canonical bundle is trivial, this implies that the fibers, or the general fibers of F, are also k-trivial, just by adjunction, because, well, the normal bundle of the fiber is trivial, and so we get that the canonical bundle is trivial of the general fiber. Okay, so let me maybe state now the main theorems. So this is joint with Stefano Filippazzi, Francois Greer, Mirko Mori, and Roberto Svaldi. So the first theorem will concern irreducible Calabi-Yau varieties. So irreducible Calabi-Yau varieties X of fixed dimension and fibered in either the class of abelian varieties, so or primitive symplectic varieties. But I'm going to take primitive symplectic varieties of a fixed deformation class. Are birationally bounded. So by this fixed deformation class, I mean, like, you should think, for instance, K3 fibered. But since I'm only fixing the deformation class, I'm not saying like fibered in K3s of some specified degree. I'm saying just fibered in K3 surfaces. And same with, yes, the abelian varieties, again, there's no polarization. There's no a priori condition on the polarization type of the fibers, okay? So that's sort of one of the strengths of the theorem. On the other hand, yeah, we only have this birational boundedness. Okay. So, but a corollary that where you can kind of strengthen from birational boundedness to boundedness is threefolds. So a corollary is that fibered Calabi-Yau threefolds, and you can also drop the word irreducible here, are bounded. And then the second theorem I want to discuss is that in the Lagrangian case, or sorry, okay, so yeah, let me explain what is a Lagrangian fibration in a second. So Lagrangian fibrations of fixed dimension lie in finitely many deformation classes of primitive symplectic variety, or maybe varieties. Okay, so this theorem B is nice because, in fact, yeah, okay, before I say that, let me say, what does it mean that I have a Lagrangian fibration? Well, it turns out that if X is a primitive symplectic variety, and I have any fibration, so this is any fibration, then in fact, the dimension of Y has to be half the dimension of X. So that's the first thing. The second thing is that sigma restricted to a fiber is 0 for all fibers. That's to say it's a Lagrangian fibration. And third, that the general fiber is an abelian variety. So that's just a general fact. If I have a fibration of a primitive symplectic variety, it necessarily takes this shape. Okay, so what's a nice sort of consequence of this? Well, there's this conjecture called the, so some people call it the hyperkähler SYZ conjecture. So it says that if X is a primitive symplectic variety and L over X is Neph, then L is semi-ample. Which is to say that, you know, the linear system associated to some multiple is base point free. And in particular, the case that we kind of will care about here is when the top power of L is 0. So the point is that if the second Betti number of x is greater than or equal to 5, then it's known that there's a certain quadratic form, the so-called BBF form, on H2 xz. Then because the Betti number is at least 5, this has to represents 0. So this is a certain quadratic form on the second cohomology. And therefore, I could deform x to some x prime with line bundle L on x prime, nef, and L to the 2D equals 0, where this 2D is the dimension, which notably is even because it has a symplectic form. And so then by this hyperkähler SYZ conjecture, that would imply that x prime admits a Lagrangian fibration. Admits a Lagrangian fibration. So, so long as the Betti number, second Betti number is at least 5, if you assume this hyperkähler SYZ conjecture, which is a big, unsolved problem, so, we're sort of not near solving that necessarily, but under this hypothesis, then symplectic varieties of a given dimension are bounded, just because you could deform any given symplectic variety with B2 at least 5 to one, which sorry, not bounded, I should say, lie in finitely many deformation classes. You're never going to get boundedness. Even in the K3 case, we saw that you don't get boundedness of K3s. You just get that they lie in a single deformation class. So you're always going to have to sort of, for symplectic varieties, you're always going to have to sacrifice that stronger condition of boundedness. Okay, so let me sort of pause there if there are any questions, maybe. Yeah. Okay.
So can I get
Oh,
this
yeah,
question?
sure.
So for the case of the symplectic variety, so we have the Lagrange vibration, so we can apply the theorem B for every symplectic variety. But for the case of the Calabi-Yau case, so
Yes,
do we have the facts the every Calabi-Yau variety has such vibrations or?
Yeah, so I don't think that there's really an expectation. I mean, people have tried to understand why or if, like, say, all Calabi-Yaus of a certain, say, shape would have a fibration. And I think it's very difficult because, so like even the case of Calabi-Yau threefolds is really the only one that's been studied. And there is this idea that if the Picard rank of the Calabi-Yau threefold is sufficiently high that maybe it always has an elliptic fibration or some kind of fibration.
Mm-hmm.
But the problem is that you're on like H2 of a Calabi-Yau threefold, and this doesn't have a quadratic form, it has a cubic form instead of a quadratic form. And so what you need is like some sort of L in there. So, I mean, this is the same as the Néron-Savary, right? Because the Calabi-Yau threefold has no H20, unlike in the symplectic case. And so now the sort of name of the game is to find, so you want to find some sort of L, which is on the vanishing of this cubic. So like L cubed equals 0 and L nef. And then conjecturally, L would be semi-ample in this setting, but the problem is that, yeah, it's not really clear why it's even possible to find a line bundle of cube 0 on the nef cone. Unlike in the symplectic case, where like somehow we have, I mean, the fact that a quadratic form of signature 2n with n greater than or equal to 3, like the fact that, or maybe 3n, sorry, with n greater than or equal to 2, That the fact that this represents zero is like an old fact from the 1800s. This is like Meyer's theorem on integral quadratic forms, whereas there's no Meyer's theorem for cubic forms. But it is something people have tried to do to show the existence of, a rational point on the null sort of cone of this cubic form. Yeah, hope that answers.
Thanks.
the question.
Thanks.
Yeah, okay, so let's
so-
discuss sort of, oh yeah, more questions?
Sorry, can I ask about the Povel of theorem? Is that the composition is unique in some sense or no?
At the moment, it's not because we've defined these primitive symplectic factors, we didn't really impose that all quasi-étale covers. Let's see. I think. It's not unique at the moment because a primitive symplectic variety could have a quasi-étale cover by an abelian variety, for example.
Okay.
But you can restrict your class of symplectic varieties to these irreducible symplectic ones, where you sort of impose that the quasi-étale covers are, yeah. And I think that there's an issue. There's sort of an issue about. I don't remember it now. I think it's about the existence of like a certain type of factor, but I thought it was about the irreducible Calabi-Yau. I'm like forgetting now. There is some sort of issue, even if you restrict your definition of symplectic variety, there's some issue with uniqueness. I thought. Maybe not. I don't know. Well, oh yeah, okay. There's always non-uniqueness because like the abelian factor has a pi1, right? So you could always pass to some further étale cover, which gives like a cover of the abelian factor, for instance, and that will change the abelian factor. Okay, so then you could ask about the uniqueness of the other factors. But
yes.
yeah, so there are some subtleties about the uniqueness. Yeah.
Okay, I see. Thank you.
Yeah, no problem. Okay, so we're gonna the first kind of key input is to approaching the theorems is this canonical bundle formula. So essentially, it's a way to relate the canonical bundle of the base and the canonical bundle of the fiber if I'm fibered in k-trivial varieties. So let me say that this is a fibration. And I don't need to assume actually that kx is trivial. I can just assume that it's trivial sort of relative to f. That is to say, kx is pulled back from the base, is pulled back from some line bundle on the base. So then the base, which is y, admits a certain natural structure called of a so-called generalized pair. I won't get into the general definition of a generalized pair, but I'll just say, like, what's the important data? Well, the important data, it's a triple where we have this y, b, and some m. And b and m are both going to be divisors, or divisor, m rather is a divisor class. So b is an actual divisor. B is an effective Q divisor. And so we can write it as some sum of prime divisors weighted by rational coefficients of maybe some coefficients a sub p, p. And what are these coefficients? These measure the singularities. So these measure singularities over p. in the sense that, you know, really over the generic point of the prime divisor P, I have some behavior of the fibration. And I'll give an example in a minute. The second is the so-called M, the sort of moduli or Hodge class. Okay, so this can be defined in a few ways. One is that, right, so I can take, so F induces a variation of Hodge structure. A variation of Hodge structure. And this M is like C1 of the G0 part of this Hodge structure. So this is the like HG0 of the fibers. So since the fibers are K-trivial, the HG0 is one-dimensional, and these one-dimensional spaces form a line bundle over the base. Alternatively, we could push forward the sort of relative dualizing sheaf, but you have to be a little careful because yeah, well, there's some subtleties involved. But here G is the dimension of X minus the dimension of Y. But we'll also see a sort of concrete way to compute this moduli divisor. Okay, so these are the two pieces of the generalized pair, and the canonical bundle formula says that the canonical bundle of X is linearly equivalent to the pullback of the canonical bundle of Y, but then corrected by these two divisors. Okay, so it's really useful to see an example of this. Okay, so let's let example. Let's let F from S to I'll just keep using X to Y actually. X to Y be an elliptic surface. So then the canonical bundle of X is isomorphic to the pullback, well, of the canonical bundle of Y plus, okay, I'll say what this By is, plus J upper star of O of 1/12. So, okay, so there's the J map, right, that assigns to Y the J invariant of the fiber. X, sorry, let me do this as little y, the J invariant of the fiber. Okay, and that's a map to P1, the J line. I pull back O of 1/12 as a sort of Q divisor class. Canonical bundle of Y, we know what that is, but then what is this By? Well, it's some way to measure like the singularities, and okay, the important point here is that if the singularities are like nodal, then there's no contribution. Okay, so if I have like something nodal, or maybe I have a pentagon or something, these will have 0 coefficient in the B divisor. But if I have something, say, like cuspidal over a point, let's say R, then I get some non-trivial contribution to it. So cuspidal curve contributes 1/6. The general formula is that it's 1 minus the log canonical threshold of the fiber. Or maybe something like I could have like a D4 fiber. And then that would contribute 1/2. Okay, so this is this B divisor. So that's this structure of a generalized pair on the base of any fibration. Okay, so how much time do I have, by the way?
I think until 11:30.
Okay, that's what I thought, right? It's a
yeah,
hour and a half.
yeah,
Okay, that's what I
45
thought.
minutes, yeah.
Yeah, okay. I was just checking that it wasn't an hour because I remember that it was an hour and a half, but it would be yeah. Okay. So all right. So yeah, let's outline the strategy. Okay, so the key sort of steps are going to be as follows. So okay, maybe a useful fact, which we're going to see here, we'll see in a little bit, is that this thing is so up to passing to some birational model of the base. Some sort of birational model, this M is Neff. And until very recently, it was conjectured also that M is semi-ample, and this was called the B semi-ampleness conjecture. But it was very recently proven by a couple of my co-authors, Mirko Mori and Stefano Filippazzi, together with Ben Baker and Jacob Zimmerman. So in fact, this M is semi-ample, though in our case, we'll see that that's kind of going to be automatic. Okay, but the point is that we need to bound, we need to show not just that M is semi-ample, but we need to bound the integer C greater than or equal to 0 such that C times M is free. We need to bound the bases YBM. And strictly speaking, I didn't really talk about boundedness in codimension 1, but boundedness in codimension 1 means birational boundedness, but where I require the birational isomorphism to be an isomorphism in codimension 1. So I need to bound these sort of triples. The third is going to be to bound, let's see. Okay, so yeah, let me also restrict for convenience. Let me restrict to the abelian fibrations. So that was the case for theorem B, right? The Lagrangian fibrations were always abelian fibrations. So then we're going to bound the so-called Albanese fibration. So this is some sort of other fibration that we're going to build out of the original fibration. And we'll bound any Albanese fibration of a fibration F from X to Y that induces this YBM via the canonical bundle formula. The canonical bundle formula. Okay, so that's the third step, and then the last step is to bound the so-called Tate-Shafarevich group. Okay, so what is this Tate-Shafarevich group? It's going to measure the birational equivalence classes of fibrations, abelian fibrations F from X to Y, inducing a given Albanese fibration. Okay, and I should say that birational boundedness, boundedness of elliptic elliptically fibered Calabi-Yau threefolds was sort of done in the 90s by Gross and Dolgachev. And this is essentially the same strategy that they used. So like if you have elliptic Calabi-Yau threefold, it's fibered over a surface. So, first they bounded the surface, the base that can appear. That's like, okay, so I guess this step one is kind of automatic, but they bounded the surface that can appear as the base, then they bounded a certain like auxiliary abelian fibration called this Albanese fibration, and then they bounded the original fibration by understanding this so-called Tate-Schaff-Ravitch group. Okay, so let me sort of explain how this works. So let's start with step one. Okay, so our goal is to bound the multiple of M, which is free. So implicitly, I'm sort of already claiming also that there is a multiple of this M, which is free. Okay, so here's sort of the idea. Let's say, so let's let F from X to Y be an abelian fibration. So then associated to that is some kind of period map. So out of this, we get so-called period map. So it's in general not a regular map, but it's a rational map from the base to some moduli space of abelian varieties. Let's say of relative dimension G. Okay, so what is this underline D? This represents a polarization type on the fibers of the abelian fibration. And yeah, what is this period map? It just assigns, it's like sort of the moduli map, right? That assigns to a point in the base the isomorphism type of the fiber. But I'm going to be like a little bit more pedantic about this. I'm going to say that a point Y doesn't go to the fiber, but to the isomorphism class of aught 0 of the fiber. So the identity part of the connected component of the automorphism group of the fiber. So the difference between sending Y to XY, of course, aught 0 of XY and XY are isomorphic for any individual point Y. But the point is that my fibration might not have a section, so there's no distinguished origin point, okay? And on the other hand, if I take the group of automorphisms that are in the connected component of the identity, there is a preferred origin, which is the trivial automorphism, the trivial translation. Okay, and this is also exactly going to be what measures the difference between X and the Albanese of X. Okay, so we have some sort of classifying map, and okay, so if we go back to this step one, well, what is this moduli?
So in this case, then how do we know that the polarization is finitely many, or is it possible to have?
Yeah, so we haven't bounded the polarization type, and that's actually going to be sort of the critical step, is to bound what types D1 through DG can kind of appear. But at the moment, we don't know what the type is, and there are infinitely many possible types. Yeah.
Okay, thank you.
Yeah. So the sort of first thing is that there's some compactification of this, the so-called Bailey-Burrell compactification. Okay. And the defining property of this Bailey-Burrell compactification is that there's some sort of universal moduli divisor. So there's like a lambda over a g d bar, which is so this is the Hodge line bundle, the universal sort of Hodge line bundle. And it's ample. Okay, so there's this kind of, it's the universal sort of line of, holomorphic volume forms on the universal abelian variety, on the over the moduli of abelian varieties. Okay, and so we have this Bailey-Borel compactification, and you could take as a definition of this M, it's just the pullback of this Hodge line bundle, okay? So we need to bound the multiple of M, which is free. We know that some multiple of it is free, sort of after we resolve indeterminacy. I'm ignoring this subtlety, but that some multiple of it is free. The technical term is B free, by the way, like B divisors, etc., if you care. But and there is some multiple of lambda, which is very ample, right? So when lambda is very ample, it's going to be base point free on AGD, and then it will pull back to something which is base point free on this Y prime, this resolution of indeterminacy. So the sort of the summary is that we need to bound the C such that C lambda is free on this AGD bar. Okay, and the issue with this is that, so the key sort of question here is why is C uniform over all polarization types? If we can answer that, if we can get a uniform C for all polarization types, then we also get a uniform C which for which M is free, okay, such that C times M is free. Does that make sense? Okay, so that's going to be why is that true? And the key sort of trick is the Zarhin trick. So the key trick is this Zarhin trick. There's a map from AGD, okay, I can put the bar if I want, to A8G bar. That's now principally polarized abelian varieties, okay? And this map, it sends some abelian variety A in here to A to the 4 plus A dual to the 4. Okay, but the polarization on A to the 4 plus A dual to the 4 is not going to be the standard polarization. It's some sort of other polarization, which is principally polarized. And now the key point is that, well, if I take H8G0 of sort of A to the 4 plus A dual to the 4, then this is sort of naturally isomorphic to HG0 of A to the 8th power. Okay, and so because of that, if I take the sort of universal Hodge line bundle on this thing, let me call this Z for the Zarhin trick. Then when I pull back, maybe I'll call the universal Hodge line bundle lambda G. And when I pull back along the Zarhin trick, this lambda 8G, I always get a multiple of this lambda G, which is the same multiple. It's independent of D. Okay, the key point is that 8 is independent of D. Okay, and so the point is that once I've taken a multiple where this lambda 8G is very ample, then that will also be a multiple on any AGD, which is very ample. Okay, and so that means that I've bounded. Okay, so that implies that I can take, I guess I can take C to be 8 times maybe the multiple of lambda 8G, which is very ample. Okay, so we bounded the multiple C for which C times M is free. Okay. So yeah, if you're curious about what happens for sort of side note, if I have, say, like a fibration in primitive symplectic varieties or K3s or something like that, then you do this same trick, but you sort of precompose with another trick, which is the Kuga-Satake. So there's this Kuga-Satake map, which goes to say the moduli from the moduli space of, okay, maybe I'll use a different D. I'll use D prime. Moduli of, say, K3s or primitive symplectic varieties of a given polarization type to, this maps to some sort of moduli space of abelian varieties of some polarization type. And then we can just do the Zarhin trick to get into AHE. And then again, the key point is that the sort of Hodge bundle on here pulls back to a fixed multiple of the Hodge bundle on this F 2D prime. Okay, so that's sort of the key input in the symplectic case. In the case where we're looking at fibrations in symplectic varieties. Okay, so yeah, we're done with step one. So then CM is free for C bounded. Okay, and now we can sort of, luckily step two is kind of immediate if you plug into the MMP literature. So there's some work of Birkar, Ducherbo, and Zvaldi that says that once you've bounded bound on C, that actually implies that you get that the bases Y, B, M are bounded in codimension 1. So I guess here the point, the key point, if you, sorry, I need one additional hypothesis here. So this is if Y is rationally connected. Okay, so that's actually an important hypothesis to have. So I'm not like an MMP expert, but what I can say about this is that like Birkar proved this big conjecture, this BAB conjecture. It said that like epsilon KLT Fano varieties are bounded for like a fixed positive epsilon. And that's kind of what's happening here. Like because the integer C is bounded, you end up getting a bound on the epsilon such that this generalized pair is generalized epsilon KLT. And then this is some extension of Birkar's resolution of the BAB conjecture to this setting of these generalized pairs. Okay, so if that meant anything to you, great. If not, I mean, I don't exactly know what goes into it either. I think it's quite technical though. In any case, why is this rationally connected hypothesis necessary? Well, like you could have something sort of silly is the problem. You could just take like, okay, take like a Calabi-Yau threefold, cross like an abelian surface, okay? And now that fibers over the Calabi-Yau threefold. Okay, so you're not going to bound the bases of such abelian fibrations, right? Because then you would be bounding Calabi-Yau threefolds. So like the key point is that this is not irreducible. Okay, and even you could imagine that maybe you would have some sort of you could make some kind of trick where you don't have the product with A, but you have some slightly like twisted product or something like that, in which case you wouldn't have, you could even make this Calabi-Yau, but it wouldn't be irreducible Calabi-Yau. So because of the irreducibility, you can't have some sort of like extra factor sitting in here. And so when you have a fibration, it's really going to be over something rationally connected. So the point is that irreducible, this is the condition that implies that the base is rationally connected. And so then in that circumstance, then we can apply the this result. Okay, so then we're done with step 2, right? We bounded the base essentially. Okay, so taking stock, we've bounded the base of the fibration. Okay, so we bounded the base. But we didn't just bound the base, we
Excuse me?
bounded. Oh yeah.
So, for the case of the symplectic varieties, then we conject as the base is always a projective space. But for the case of Calabi-Yau case, so the base space is various types or.
Yeah, so that's a good question. So yeah, conjecturally, if the base is smooth, and the total space is smooth for the symplectic case, then the base is conjecturally projective space. Or sorry, it's known that if the base is smooth, then it's projective space.
Yeah.
Wong's theorem. But yeah, and it's conjectured that if the total space is smooth, then the base is projective space. But in general, yeah, like I don't know. I mean, I don't know exactly what can be said in general about the base of Calabi-Yau, like say irreducible Calabi-Yau, like beyond rationally connected. I think that there are examples over, irrational bases. I think you can sort of set it up, like by finding, say, a Weierstrass equation of an elliptic fibration over a Fano threefold, which is irrational. I think it's possible.
But at least the rationally corrected.
Yeah, but it's rationally connected because of this result. And that sort of follows from the fact that if it wasn't rationally connected, you could take the MRC quotient and it would be some sort of K wouldn't be pseudo-effective, and you would get a fibration over something where K isn't, where K is pseudo-effective, and then the canonical bundle formula for this fibration would give you a contradiction to the irreducibility, essentially. Okay, so that's sort of a rough outline of the proof. And then yeah, so the symplectic case is similar. You can we don't know what the bases are in general, maybe there's a conjecture, but for sure they're always rationally connected. And in fact, we know a lot more about the bases in the symplectic case, right? Like they're rational homology CPDs. So they at least have the same cohomology and Hodge structure as projective space. Okay, so we've bounded the base. And now what do we need to do? We need to bound the fibration. And how do we bound the fibration? Well, we need to bound the period map, right? And to do this, we need to bound the polarization type. So we bounded both the base and, I should say, we bounded the whole triple, and B and M. Okay. So yeah, that's actually important that we've bounded these divisors. We've bounded the entire triple. Okay, so now here's sort of the next step. Okay, yeah, what do I want to say? Right, so yeah, so here's sort of the strategy. We're going to compose the period map with the map to so now we take the Zarhin trick and we get into A8G. Okay, and the first thing we're going to do is bound this map. We'll bound this. And how do we bound, we could call this, I was calling this the Zarhin-Tricht period map. So the point is just that we have this lambda 8g on here, right? And so if I compose the Zarhin-Tricht with this period map, then I get 8 times this divisor m. And so the point is that because I've bounded this divisor, and this is now just a target, a fixed target, and this is just some fixed ample line bundle on it, essentially what I'm doing here is bounding the volume of the map. So I'm bounding, this bounds actually z composed with phi. Like, because essentially I just take the graph, right, of this period map in the product of y with AG. And because I know some fixed ample line bundle pulls back to some fixed specified bounded line bundle on the source, y, that actually bounds the volume of the graph. And so then by like a Hilbert scheme or Chow scheme argument, this period map is bounded. Okay, but there's actually a very sort of subtle point, which is that this is bounded, but in general, we can't a priori bound phi from z composed with phi. Okay, so here is a sort of stupid example. This is an instructive but stupid example. So what we'll do is we'll just take an abelian fibration over a point. Okay? So this is, let's say, an abelian surface over a point. Okay, so what is the period map of such an abelian fibration? Well, the point maps into some sort of A to D. Okay? And now if we take z composed with phi, well, we get a map from the point into AHG. Okay, and it's true, the space of points maps from points into AHG is bounded, right? Because AHG is just some single variety. But there are countably many different subvarieties of AHG that we're trying to factor this map through. So it ceases to be bounded once we require that it factors through one of these countably many subvarieties, okay? And so these are bounded, right? But these are not bounded because we haven't bounded the polarization type. And so the key point is that, well, if this z composed with phi is bounded, then the pullback under z composed with phi of the universal rank 16G local system, so this is like H1 of the fibers over A 8G. Okay, so this is some z to the 16G local system. So then this is bounded. And that actually implies that the original z to the 2G local system is bounded. So if I take R1 F lower star z, this is a z to the 2G local system is bounded. And that indeed happens in our dumb example. The local system is the trivial local system because we're on a point. And then we get a trivial local system of rank 2G, and there's only one of those. So the local system is bounded. And now here's the kind of key, the key point is that, okay, so we've bounded this local system. So therefore we've bounded like wedge 2 of this local system, which is like the H2s of the fibers. Okay, so this is also bounded. So they say on Y, and which on a bounded family of varieties. And then therefore the space of global sections of this is also bounded. So the key point is that, so these are the monodromy. These are bounded in a space of sort of alternating two forms on Z to the 2G. So these are the monodromy invariant symplectic forms on, let's say, H1 of the fibers of F. Okay, and now here's the sort of key point. Well, there's this Deligne theorem of the fixed part. This implies that this thing actually has a pure weight-2 Hodge structure, which includes into like H2 of XZ, okay? And when you're sort of a Calabi-Yau variety, this Calabi-Yau condition, it implies that H20 of X is 0, okay? And so that shows that all of these monodromy invariant classes, these are all of one type with respect to the sort of pure Hodge structure that I mentioned from Deligne's theorem. And therefore, since we bounded this local system, we've also bounded the type of an alternating two form of one type. So in other words, we bounded a polarization type. So then we bounded D. Okay, so that worked in the Calabi-Yau case. Oh yeah, maybe I should put this. Okay, so then this implies, maybe I'll put star here. These star are all of one type, and then that bounded the D. And now in the primitive symplectic case, okay, so H20 is not 0, but the condition that the fibration is Lagrangian implies that H20, you know, let's say a sigma in H20, satisfies that its restriction to a fiber is 0, right? Satisfies that sigma restricted to a fiber is 0. Okay, and so then that implies the same result. So any monodromy invariant element of this local system is of one type, and therefore this again allows us to bound the polarization type. And then so replacing AAG with AGD, we've now bounded this. That's sort of the critical thing. And now we just redo the volume argument, using the fact that the pullback of lambda is M to bound the original period map. So then this is bounded. And finally, because we have that being bounded, then the pullback of the universal family is bounded. And the subtlety here is that the pullback of the universal family is not actually X. That's because this classifying map did not send Y to the fiber, it sent it to aught0 of the fiber, okay? And so rather, the pullback of the universal family along the period map is equal to this X alb over Y, whose fiber over a point is this group of translations of the fiber. So you can build some abelian fibration with section by looking at the aught0s. Okay, so then I think we completed step 3. We bounded this Albanese fibration. And let me call this F alb. All right, so yeah, that was maybe a lot. Maybe I should pause just for a second, ask if you guys have questions. And then, yeah, I can say a couple words about how to bound the torsors. Any... Okay, all right, so... Okay, so yeah, maybe I'll discuss this Tate-Shafarevich. So yeah, the key point is that because we could bound the map to AHG, we could bound, yeah, this local system, and then we could bound a polarization type from this local system. And yeah, that's where the sort of hypothesis that it's irreducible Calabi-Yau or symplectic comes in. Because otherwise the theorem is not true, because you would have an abelian fibration over a point. And those aren't bounded. Okay, so here's sort of the picture. Now I have some kind of abelian fibration. Let me draw it. Okay, so I have my base y, right? And now I have this x over y. And my original map F. And maybe I have some sort of nodal fibers or cuspidal fibers. I could even have multiple fibers. Some sort of not so well-behaved necessarily abelian fibration. Then I have this other fibration. And this is going to be my X-alb. And this is like F-alb. And the key sort of point, the sort of key difference is that F-alb has a section, right? So it has some sort of zero section. So in particular, you know, it doesn't have multiple, it doesn't have, say, irreducible multiple fibers, right? Because then we couldn't have a zero section, because of the intersection number with the multiple fiber. So, okay, maybe, yeah, here we have something more like this. Okay. And now the idea is that F may not admit a section. Okay, but by going to some sort of G Galois base change, like for some G Galois base change, then we can kind of get rid of multiple fibers. And sorry, I meant yeah. F may not admit a local section even. Like there's no local section of F like through this double fiber. It's impossible for intersection number reasons. But it is possible, like if I look at where this point goes, right? And then I made some sort of order 2 ramified base change, like which is ramified over this point, then it is possible to get a family which has a section, a section at least locally. Okay, so this is like my y tilde, and this is y, and this is my G Galois base change. Okay, so essentially what I do is I clear the multiple fibers, and so for convenience, I'm just going to pretend that, and then the solution is to work G equivariantly and do everything G equivariantly, and that's kind of technical. But so let me just elide that technicality and assume that so by working G equivariantly, essentially, we can assume, let's just assume that X over Y admits a local, okay, let me say a local rational section. I'll be a little weaker. Okay. Okay, so now we have, so I'm just gonna erase this double fiber because now we don't have a, okay, now we've cleared the multiple fibers. So we have this local rational section. Okay. So like over some sort of cover, you know, we have like over an open set UI, I have a section, you know, and then maybe, okay, over a set UJ, I have a section, right? Okay, this is my section over here. And so the point is that when I have a section, X So X is isomorphic to X alb over the locus where I have a section. So X UI is isomorphic to X alb UI because X has a section over UI. We should also work in the étale topology, whatever, doesn't matter. And so now using such an isomorphism, what I get is like an element of H1 of Y with coefficients in like X alb in some sense. So this is some sort of abelian group scheme. Over Y. Because like what's happening is that on the double overlaps where I have like UI intersecting UJ, I have two different sections, right? And so then I can just compare these two sections. The difference between these two sections is an automorphism in the identity component. So that's the translation that connects one section to another. And so I get some sort of Tij in here, and then they define a cocycle. So this ends up exactly measuring, this exactly measures the birational isomorphism class of X. Okay, and so this is what we sort of call this Tate-Shafarevich group. So yeah, essentially it's like it's an abelian group scheme, you know, whose fiber over a given point is the group aught 0 of that fiber. Okay. And there's some, of course, it's subtle because like that works fine for smooth abelian fibers, but for singular ones, it's not as well behaved. But just to give you some examples, maybe if I have some smooth elliptic fibration and then it degenerates to a nodal curve, then the fiber over this thing is just this elliptic curve. Over this point, it would be C star. But I might have something like a triangle, in which case it would be like C star cross Z mod 3. Okay, so that's sort of, that's what this X alb as a group scheme. And the key point is that, so it's sort of the technical term is that it's semi-abelian, which is to say it's like some extension of C star to the, say, G minus H, and then I have some group scheme, okay, X alb over a point P or something, and then an abelian variety, I don't know, A. So over P in Y. And then this is an abelian H-fold. So again, my original abelian fibration may not have this behavior where I have this semi-abelian group scheme, but it does after some finite base change, finite Galois base change over a big open set. Okay, and so then a careful analysis of this shows that this group is finite. The key point is that this Tate-Shafarevich group, it kind of fits into some kind of exact sequence where, so here you end up with H2 of XO mod H2 of XZ. Okay, so it has some sort of identity component, and then it has some sort of finite torsion component. And again, the key sort of condition that's coming in is that because you're irreducible Calabi-Yau, that implies that this sort of continuous factor is 0. And so you only end up with this finite torsion component of the Tate-Shafarevich group. And in the case where it's primitive symplectic, there is legitimately a sort of infinite number of these twists of the abelian fibration, of the abelian fibrations with a fixed Albanese, but they all lie in a single deformation class, analytic deformation class. And then using that they lie in a single analytic deformation class, you can use some arguments about, the Torelli theorem for symplectic varieties due to Bakker and Len to say that the algebraic ones are all deformation equivalent. Okay, so I guess it's 10:30, so I should stop there. Thanks.
Yeah, so are there any questions?
Hey, Phil, can you hear me?
Yeah.
Hey, this is Zach. How's it going?
Oh, hey. Yeah,
Hey.
I recognized your voice. I
Oh, cool.
couldn't see you because the screen is a bit small, but oh no, I'm
Okay.
zooming in now. Yeah, there you are. Okay, nice. Cool.
So maybe, I don't know, this is maybe kind of a superficial question, but I'm wondering about the connection here to the number theoretic Tate-Shafarevich group, where finiteness of that is a very hard theorem.
Right.
Like,
Yeah. So there's I feel like the general sort of principle in all those things is always that the arithmetic analog is always way harder than the geometric one, So usually the courses of things is that first it's proved in the geometric setting, in varieties. So that would be say over a function field of a variety in characteristic 0, then it's proved for a function field of a curve in characteristic P, a global field, and then it's finally proved for number fields or something. But the premise is similar, which is that I have spec Z, right? And this I should think of as a curve, right? And then okay, and then I have sort of the generic point or something, spec Q. Okay, and now I have some sort of elliptic curve. And okay, so the Tate-Shafarevich group by definition is okay, so you take so we're going to take H1 of okay, God, I hope I don't mess this up. So I take H1 as spec Q with coefficients in E. So you should think of this is the abelian fibration over the generic point, and then this H1 exactly measures the twists of this abelian fibration, this elliptic curve, say. So these are varieties which are not elliptic curves over spec Q. They don't have an origin point, but their Albanese variety is the fixed elliptic curve. Okay, so it's the things whose Albanese is this elliptic curve. And now you can base change this to spec Q nu, where nu is some place, right? Of Q's, like a p-adic field or R, right? And then you get some sort of E nu, right? Which is the base change. And the Tate-Shafarevich group is the kernel of this map from here into the product over all places of H1 spec Q nu, E nu or something, I hope. So what is it saying? Well, okay, by restricting the elliptic curve to this place, you should think it at the prime P, I'm taking kind of a little neighborhood of P. And then I'm saying that the abelian fibration should be trivial in that neighborhood of the prime P or something. So it's sort of the things which are sort of locally, it's literally things which are locally isomorphic to the elliptic curve E, in the sense of locally being that I, go to each place of Q. And then I require that my twist of my elliptic fibration is a trivial twist at each of those places. So that's, I think of that as kind of being similar to the statement that sort of there's an open cover of the base where the fibration has a section and therefore is isomorphic to its Albanese fibration, And so I don't know. That's kind of the and then the fact that kind of you have these multiple fibers and stuff, like that's sort of like relating, you can kind of throw away finitely many primes. I mean, which is true, they're literally primes, right? In the sense that they're prime divisors on Y. So like the primes there and the primes here are kind of analogous. But yeah, I mean, it's just an analogy. And like if you think about Tate-Shaw, okay, so it's funny, I was literally thinking about this today. The key property that implies that sort of the Tate-Shaw-Fravich group in our setting is finite is this, that H2 of XO is 0, okay? But this is kind of like the total space, right? So what here is the total space? Well, it's like you have to think of E over this curve, but over like spec F1 or something. Okay, so this is like a surface, right? And what you need is that H2 of this surface, like O, like over F1 or something, is 0. Okay, this is a bit of a hacky analogy, sorry. Yeah.
Okay.
I don't know.
So we get something that's closer to like a function field analog of a theorem for finiteness rather
Yeah,
than
exactly. So like you could replace this Z, exactly. So if you replace this Z with spec of like FP adjoin T, then you're really, I mean, then this is better, right? Because this is really like a curve. You know, this is like A1 over, you know, FP or something. And then I have an elliptic fibration, and then, yeah, I'm saying something about, well, I'm saying that sort of that if I look at the sort of completion of at a point that I have like at least a rational section, right? I'm only doing it over the generic point. So yeah.
Cool. Thanks.
Can I ask a question about the Zahin's trick?
Oh
So,
yeah,
so you
sure.
can go from the moduli of abelian varieties with some polarization type to PPAVs, like the moduli of PPAVs. But like, how difficult is it to go back? Like, if you fix a polarization type, is it easy to know like if a PPAV can be factorized into an abelian variety of that specific polarization
Right.
type?
Yeah, that's a good question. I think, I mean, this map is finite for one. So, but it is legitimately sort of non-trivial because like, for instance, here's like a silly example. Let me take A plus B. Okay, so then that maps to like A to the 4 plus A dual to the 4 plus B to the 4 plus B dual to the 4. But like this Z of AB, this is going to equal like Z of A dual plus B, for instance. Right? So there are sort of legitimately different abelian varieties that might kind of get glued together by this Zarhin trick, but it is finite. And then I feel like it's kind of hard though to know if I just take some random abelian variety in here, I don't know, X, or not X, whatever, C. If I take some random abelian variety in here, yeah, it's not so clear how exactly to find, yeah.
Okay, yeah.
Yeah, I'm not sure.
Mm.
Like we came up with a way to undo the local system, but I don't know exactly how to undo, like, I don't know exactly how to undo the Zarhin trick itself. Like one worry that you could have is that given a C, there are actually infinitely many different abelian varieties that it's the Zarhin trick of, and it's the infinitely many is not coming from the fixed. I mean, because of this sort of, for fixed D, the fact that the map is finite tells you there's only finitely many, but maybe there are different polarization types that all give you kind of the same abelian variety. So yeah, I did think a little bit about it, but I wasn't able to like figure out whether
Okay.
sort of.
Yeah, thanks. Oh, so this map is like, it also extends to the Bailey-Burrell compactification.
Yeah, that's
Okay.
right. Because sort of maps like this that come from, they in some sense come from like the Hodge theory or the group theory. Like there's in general these period domains are of the form like GR mod a maximal compact subgroup and then mod some sort of arithmetic lattice. That's sort of the general shape of these period domains. And it's like when you have a map that's induced by like, you know, by groups kind of like this, you know, sending the lattice to the lattice. I don't know, lambda H to lambda G, and then the compact to the compact. Yeah, so like these maps are, they extend to the Bailey-Burrell compactification because the Bailey-Burrell compactification is sort of built from this group theory type data. It's sort of functorial. Yeah.
Okay, I see. Thank you. And the last question, so like you say, like if we assume the SYZ conjecture, then we can show that the primitive symplectic varieties lies in finite C many deformation classes. So have any people tried to realize these deformation classes?
You
And
mean
what do
like
they
to try to
find?
explicitly bound them?
Yeah, like
Yeah, I mean, not using these techniques, but because this is hopeless for getting an actual bound. Like there's many steps in the proof that are really like not very effective. So here's a really bad one for yeah. A really bad one for like getting an effective bound is this, like this BAB thing. It's like you would need to sort of explicitly know. First, you need to explicitly bound this C, and then you would kind of, so that's already very difficult, saying like what multiple of the Hodge line bundle is like ample on AHG. You know, that's something about modular forms or something. And then you get a bound for epsilon for the epsilon KLT, and then you would have to extract an explicit bound of this resolution of the BAP conjecture. And that would sort of only bound the base, and then bounding this map, you use a Hilbert scheme argument. So it's sort of, you use an abstract fact that, you know, the Hilbert scheme of bounded Hilbert polynomials or cycles of bounded volume are bounded. But like, I feel like that's never particularly effective. Maybe like in projective space, when you look at like super low degree subvarieties, you can say something explicitly about the Hilbert scheme, but you know, beyond that, like you're never going to be able to say like, even if G is 1 or something, you know, you're never going to be able to say something about the Hilbert scheme of A8 bar. So okay, so this is just to say that this is not the right technique if you want to sort of explicitly bound them. I don't know of a strategy. Yeah, I don't think anyone has really a good strategy for finding like an explicit. Maybe for fourfolds. Like for fourfolds, it's not so bad. Like you know the base is P2 and it's abelian, you know, you have maps to abelian surfaces and yeah. So maybe it's less bad for hyperkähler fourfolds.
okay, thank you.
Yeah.
Are there any other questions or comments? Okay, if not, then let's thank the speaker again.
Thanks. Yeah. Thanks for listening.